It's organized by NAISS and ENCCS, and myself, I'm situated at NSC, and we also have help from Uppmax. And I thought maybe not everyone is familiar with NSC, so where I'm working. So I thought maybe I'll just tell a little bit about us. So we are the National Supercomputer Center at Linköping University. So we are part of Linköping University, and we are also part of this national academic infrastructure for supercomputing in Sweden. So we have some academic resources for NAISS. And some of you will work on that resource in the afternoon on the Tetralit supercomputer. But we also have different kinds of partners apart from Sweden academic, and that is Saab, who is mostly working within the defense industry, for instance, with aeroplanes and submarines and such. And otherwise, we have a close collaboration with the Swedish Weather Forecasting Agency, so SMHI. And from more recent years, we also have a collaboration with the Norwegian corresponding organization, so to say, so also a weather forecasting agency, but in Norway, so Meteorologisk Institute, or Met Norway. So we have several academic clusters, and as I already mentioned, Tetralit is a NAISS cluster, so it's open for all researchers in Sweden can apply for projects and run on Tetralit. As we can see here, it's getting a bit old. So it was built in 2018. And next year, there will be a replacement, or well, effectively, it will be a replacement of Tetralit with the new Arrhenius EuroHPC supercomputer, which will be located here at Linköping University. So that will be the new resource. Also, we have a local supercomputer for our Linköping University users, and that is called Sigma, which is in practice identical to Tetralit, but a bit smaller, rather around 100 nodes instead of around 2,000 nodes. And there is a third academic cluster for Swedish research, though it's not within the NAISS organization. So this was a grant from the Knut and Alice Wallenberg Foundation, but all researchers in Sweden are welcome to apply for projects on this Berzelius cluster, though it's mainly intended for artificial intelligence and machine learning. As you can see here, it mostly contains an NVIDIA GPUs, so A100 GPUs, which is, by the way, the same type of GPUs as you can find on the Leonardo system, which some of you will work on in the afternoon. And here we can also briefly note that if you look at the top 500 supercompute resources in the world, Tetralit started at 74, but now it's slowly dropping out of that list at 282, but it's not a big surprise since it was built in 2018. And hopefully Arrhenius will be relatively high on that list at least, but we will see. Okay, maybe I should present myself. So my name is Vein Olofsson, and I had a PhD in physics 2005 at Uppsala University. I was a postdoc at Kyoto University in Japan for some time, and thereafter at Leoben Montana University in Austria for roughly 1 year. And after that, I came back to Sweden, and I started actually as an application expert at NSC already from 2011. Well, at that time, it was half my position. And somewhat later, I mainly is focusing on working as an application expert. So now I'm working in 90% here at NSC. I'm still working a little bit with physics. So my area is theoretical spectroscopy for the core level region, so the X-ray region. And of course, for me, it was a bit interesting that in the newer versions of VASP, you can now actually compute X-ray absorption spectra. So at least I found that a nice addition to the VASP code. And my focus has been electronic structure calculation, so using density functional theory codes. So here at NSC, typically I help with many user questions around VASP, but also, of course, installing VASP at the center and maintaining it, doing some benchmarks and testing and so on. And on the one hand, there are many VASP-oriented questions since it's such a popular code, but one shouldn't forget there are also other codes out there, like Quantum Espresso, V2K, GPO, Siesta, and ELK and Exciting Code, and so on and so on. And there are also other PAW codes, so I will show some brief examples later on. Okay, so about the schedule for today. So I think you have already this information through the links, which has been shown, for instance, in the chat. But I thought I just repeat a little bit. And how I like to do this kind of workshops is to have frequent breaks, because otherwise I will get a bit tired to listening to my own voice, so to say, hour after hour. So I would like to have a break at least 10-15 minutes every hour. And I think that is good, so one can get some coffee and other refreshments. And we also have 1 hour lunch breaks. And as you can see here, we have now before lunch, we have 2 presentations, and tomorrow we have 2 more presentations before lunch, so before going to the hands-on sessions. And I could already mention now that for tomorrow's schedule, the third presentation in the workshop, Running and Performance, that will actually be quite much longer. So that will be the main part of that whole morning session, because the final presentation, Utilities and Summary, that is more showing the smorgasbord of all the different tools which you can use for pre-processing and post-processing and working together with VASP. So that part will be much more brief. Okay, so I will try to quite strictly enforce these breaks, because otherwise I will be too hungry if I continue to talk after 12, for instance. Okay. Just a little bit about the workshop organization. I think you've seen that also on some other page. And we are mostly people from NSC, ENCCS, and also UPMAX. And some of us have been working quite a lot with VASP. So it could be that we could even answer some question if you have some specific question, if there is some certain area you're interested in or which you are going to work with. At least we encourage you to, you can type down your question in in these links which was sent out, with HackMD. Of course, we cannot guarantee that we cover the whole area of physics and chemistry, of course, but that's how it is. At least for myself, I could probably answer if there are some questions, for instance, about X-ray absorption spectroscopy, since that has been my area of study, so to say. Okay, so about this VASP Best Practices Workshop. Well, we will now in this first part, we will go through some basic theory for a projector augmented wave method. But it will be on a really basic level. And if you're interested in a more, so to say, solid background, then you have lots of resources from the VASP developers, for instance. They have their own VASP channel on YouTube, I think. So here, but for completeness, we will cover, or I will cover that area briefly at least. And we concentrate on general considerations and questions which are a bit more specific to running VASP at a supercomputing center. And we will focus on the practical aspects of running VASPs in this workshop. And we will have a look at the influential parameters like NPAR, NCOR, ALGO, NSIM, KPAR, and so on and so forth. And I will also demonstrate the different benchmarking type of examples or tests and or experience of running VASP. For instance, also running on the CPU and GPUs. But that will be in the tomorrow sessions, most of the benchmarks and these discussions. And also for tomorrow's session, I will go through some common or very typical problems which one might encounter when running VASP. And all these presentations are available so on the VASP Best Practices Workshop Git page. And if you download them, you will find that everything which is underlined is a clickable link, which will take you hopefully somewhere useful. For instance, it can be a description of a certain parameter in INCAR or a reference to some published paper. And if it doesn't take you somewhere, then it's probably something wrong with that link. Yeah. Okay. So resources. So that is quite important, in particular if you are starting with using VASP. So I really recommend to have a look at the VASP wiki and manual. Here you have lots of examples and tutorials, and you have a very detailed description of each parameter which you encounter, for instance, in INCAR. And you can find all this information at the VASP main page at vasp.at. So have a look on these resources in detail, and they are also searchable. So here one can find really useful stuff. And also you can find the presentations from the VASP developers. So they have put up lots of resources there. So you can find some of their presentations in form of PDF files, which you can download and have a look at. And also, I think there should be a link to YouTube presentations which have been put up there. And they will typically go much more into detail, in particular for the theory part. So here we will take a more basic approach for theory and just consider the main things, so to say. So it's a very useful resource. And if one happens to have some problems with VASP, it's extremely useful to have a look at the VASP forum. And then you have a proper VASP license set up for you. You can also log in there. And if someone has uploaded files and stuff, you can download this when you're logged in to a forum. And what is good with VASP is that, or one of the good things is that there are quite many users of it. So it's really quite common that if you have a problem, you are probably not the first person ever who had that particular problem with VASP. So at least most of the problems I've encountered has been found there. And it's also a good place if you really find a bug in VASP. Here you can also upload that information directly to the VASP developers. So that is their preferred way of interaction with the users, I would say. Okay. Yeah, and as I mentioned in the last presentation, I will go through some more of these resources, typically different programs and codes which can be used together with VASP. So pre-processing, post-processing, and so on. And one of my old co-workers here at NSC, Peter Larsson, he had a blog and there he put out quite much information about running VASP. Though one should note that it's getting a bit old now. I think it's almost 10 years. So some things might have been updated, of course, with VASP. And nowadays, Peter is working with the LUMI support for Sweden. So if you are a NAISS researcher in Sweden, then you know that the NAISS has a part of LUMI. And Peter is involved with the user support for the LUMI for the Swedish researchers. And also at NSC, we put some information about our VASP installations. And that is, of course, very useful if you are a researcher within a NAISS and you are going to run VASP there on Tetralit. And maybe there might be some other useful descriptions there, even if you don't have access to Tetralit. And of course, if you are a researcher with a project at NAISS and you have some problem on Tetralit, you're always welcome to contact us to the NSC support. Okay, so that was a brief start, so to say. And now we go to the real first part, I guess, so introduction and some basic theory. Yeah, so this was just a reminder about who is organizing. Okay, so a short background for VASP. So it's a PAW method, so projector augmented waves. And it's basically for density functional theory calculations. But it's also possible to do post-DFT type of calculations. For instance, within many-body theory, so you can do GW approximations. And if one consider exchange correlation functional, there are also hybrid functionals, for instance, mixing in exact exchange. So that could also be considered like a post-DFT method, probably. Sorry. And we also have a Born-Oppenheimer molecular dynamics. And this might not be a big surprise, but VASP is quite widely used in academia and industry, and probably most of the people attending this workshop has probably already heard a bit about the VASP and maybe used it a bit already. And since it's such a widely used code, there has also been efforts both from Intel and NVIDIA to help with the optimization of VASP so that it can use the hardware better or more efficiently. In particular, one could mention that considering Intel, I think they helped with the OpenMP threading possibility with VASP, which was officially introduced with the new VASP 6 versions. And with NVIDIA has, which might not be a big surprise, helped with the GPU version of the VASP code. And that is using OpenACC for running on GPUs. And that is, of course, very good for us VASP users, that there has been this investment and concentration on getting VASP to run really efficiently on different types of hardware. And if we look locally here at NSC and we check the tetralit supercomputer, at each time, if you check what is running on tetralit, about 20-25% of the whole supercomputer is running VASP. So it's probably the number one software which is running on tetralit. Of course, this depends also a bit on the different research areas which are running at different clusters. Let's say if it would be an AI machine learning cluster as Perseus, and their requirement is that actually that it should be related to these topics, then there are very few or no VASP calculations running. But for regular resources for NAISS, quite many people are working with materials research, so both from the more physics side and quantum chemistry side. And since we have so many users from that area, it's quite natural that a substantial part of the cluster is running VASP. So in that sense, it's not a surprise. Okay, but I promised a little bit of theory, so we can start with the Schrödinger equation. So here we can see the Schrödinger equation, and well, so we have an equation, but now a very practical question comes, and that is how to solve this equation. So we know that for a solid, we typically have 10 raised to 23 number of particles, and that seems to be a bit too much to chew on, so to say. So we need to make this equation easier to solve somehow. One very typical approximation, which one do already at the outset, is to use the Born-Oppenheimer approximation, meaning that we set the term related to the movements of atoms, of the ions movements to zero. So we consider a frozen system where we are not including the vibrations from start. Okay, so that's a start. So we have this Schrödinger equation, and now we just have to solve it. And it was already noticed by Dirac. So in his words, the general theory of quantum mechanics is now almost complete. The underlying physical laws necessary for a mathematical theory of a large part of physics and holochemistry are thus completely known. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be solvable. If therefore it therefore becomes desirable that approximate practical methods of applying quantum mechanics should be developed, which can lead to an explanation of the main features of complex atomic systems without too much computation. And that was, of course, very, very insightful there already at the beginning. because it doesn't really help us if we have an equation, but we don't really have any practical means to solve that equation. And that is where density functional theory comes in as a very successful way of trying to solve this. So the idea with density functional theory is that instead of looking at these wave functions, where we need to consider this 10 raised to 23 number of particles, instead we can use the electron probability density. And you have some famous papers by Hohenberg and Kohn and Cham. And what we have here, if the potential of a system is determined uniquely, except for a constant, by the ground state density, then we can have the total energy function for a given potential, that it assumes its minimal value for a correct electron density of a ground state. So we have an ansatz here for the total energy. And I will not really go so much into the details of the theory, but I will try to highlight the most important aspects. And that is that the complicated things has now ended up in a single part here, which we will look at on the next slide. So the exchange correlation part. Well, actually, we will look at that a bit further on. So let me now compare the different views here. So we started on the left-hand side with, so to say, Schrödinger equation view, where we had this very hard problem to solve. So we have all these many electrons, if we want to simulate, let's say, some bulk metallic systems, and they are moving in an external potential. But instead, we can consider these non-interacting Kohn-Cham particles or non-interacting electrons, which are moving around in an effective potential, which is different from these external potentials. And the nice thing here is that these two approaches are formally equivalent, so we can use the Kohn-Cham way of solving the properties of our systems. And if we are looking into this effective potential, which we end up with, we see that we have these terms, that we have a term there, which depends on the exchange correlation functional. And we can think of this, that we have put everything which is difficult, so to say, into this exchange correlation functional. So, but everything else looks kind of nice at the moment. And what was actually a surprise at the time was that if you take one of the most easiest, so to say, approaches to describe an exchange correlation function, that is just starting out with a homogeneous electron gas. So the local density approximation. And it turns out that this is actually extremely efficient and works very, very well in many cases. And there was nothing really from the start which might have led you to expect that it would be this way. But on the other hand, it turned out that if you still would like to improve on the LDA, then it became more difficult. So getting better exchange correlation functionals turned out to be much more work. And it took some time before one had a bit more advanced such GDAs which worked well. And if you are already a user of VASP, you might know already that the typical default which is used in VASP is the PBE GGA exchange correlation functional. But of course, it's not the only beyond LDA exchange correlation functional. Nowadays there are really many. Though one should be a bit careful how to select them, and I would say that typically PBE GGA works very well in most cases. But there might be some specific situations where one would prefer to look into using some other exchange correlation functional. And you also have the ones beyond GGA, so meta GGA, for instance. And I also briefly mentioned before that we have these hybrid functionals where you have some mixing with the exact exchange. And a common one which is used quite much with VASP is the HSE06 type of hybrid functional. Okay. And now I'm jumping a bit here. And if you remember, so we want to simulate a solid. And a problem was that we had so many particles. So it's a bit tricky to how to describe it. But it turns out that when we have these very periodic systems, which is just, let's say, a unit cell, which is repeating forever in each direction. Or I mean, in reality, it's of course a finite system, but on the other hand, it's so many of the particles, so in practice, we can consider it as an infinite system. Well, it turns out that it's possible to use the block theorem, and we can have a look at the one electron wave functions. And it turns out there are some very simple relations here that you can just use this description of the one electron wave functions, which are completely described by their band or the principal quantum number and a point in reciprocal space, so the inverse of real space. And I will come back to that. So it's possible to, instead of looking at this single wave function, which is describing all or 10 raised to 23 particles, to instead look at these one electron wave functions inside a unit cell by going via the block theorem. And if you want to have a more detailed look on this, I recommend the presentations by Marshman, one of the developers of VASP. And I try also to put all the links in these presentations. And I think the links should still work. So if I want to have some more details, so please look at these links. Yes, and here is just a quick demonstration for, so this looks like a face-centered cubic cell. So on the left side, we see it in real space. And on the right-hand side, we can see the reciprocal space instead, so the inverse of the real space. And we also see the first Brillouin zone of the FCC here. Okay, a little bit about the overall iterative calculation. So how one in practice run VASP calculations, and also more broadly in general other DFT codes. And that is that we start with some trial charge and trial wave vectors. So there are slightly different ways exactly how to start. But the idea is that one uses some certain algorithm, which one also can select. So for instance, with VASP, you have different type of algorithm which you can select in this stage. And some of them have the properties that they are quite fast. But it can also depend quite much on your particular type of structure which you want to solve, how easy different algorithms might work. So this can be a cause for problems sometimes. And what this scheme shows is basically the how to minimize the total energy. So if we remember, if we go back, we have that the total energy function for this given potential assumes it's a minimal value for a correct electron density of a ground state. So we are kind of iteratively getting closer and closer to this ground state. And in this scheme, they also have this outer loop where they say calculate forces, update ions. But that is only if you also want to completely relax your structure. So meaning that your atoms have the possibility to move around so that you can find the structure which minimizes the total energy. But that is also a very common use of VASP. I think if you remember yesterday's presentation, I think there was a comment there that also for the EMTO calculations, it was quite common that you start with VASP and you do a structure relaxation, and then one uses this structure, but you use another DFT code. And for instance, I was using quite often VINTO-K to compute X-ray absorption spectra, but it was quite common that as a first step, I would take a structure and relax it using VASP, and thereafter take this structure and insert into a VINTO-K calculation. So this is a common use of VASP, I would say. So even if one is interested in using other DFT codes. Okay, but why PAW? Well, one of the original goals was to have both a method which is very accurate, such as LAPW, so linear augmented plane waves. So typically this is full potential codes, including all electrons. But one wanted to combine this accuracy with a method which is very fast. For instance, like using ultrasoft pseudopotentials. But here one wanted to keep the all-electron wave function because, well, that's where you have the physics and chemistry, so to say. So we would like to keep it if it's possible. But one can do some approximations. For instance, it's typically the valence electrons which partake in the chemical bonding. So for most purposes, you can freeze the core electrons. So we don't need to treat them explicitly in the calculations. Though I should mention, it's actually possible to, if one want to, one can of course include them. And with VASP, you also have a possibility, if you're interested in core level spectroscopy and core level binding energy shifts, it's actually possible to recalculate the core electrons in some extra step in the VASP calculation. Okay, so we want to have fast calculations, and this is possible to do in the reciprocal space using plane waves, because then one can use so-called fast Fourier transforms. So there are equations which are very suitable for plane waves in reciprocal space. And combining all this, the goals and what we want to do, a solution is the projector augmented wave method. and a little bit about plane waves and augmentation. So a problem if we are when looking at plane waves is that if we are very close to the nucleus, so to the atom, we will have very rapid wave oscillations just at the different atomic sites. And also at the atomic sites, which is not a big surprise, we will have strongly localized states which are staying there. So even if we are just looking at valence electrons, we still have very strongly localized state. So one idea is to split the whole space into interstitial and augmentation sphere regions. And in the interstitials, where we can have only smooth plane waves, which should be very easy to handle using the different algorithms. And we also have a criteria that we don't want to have any overlap between these augmentation spheres. So we are using a so-called one-center expansion. And in PAW also the wave functions are independent on both energy and potential. And here is the basic scheme for the PAW augmentation. And I will show this in slightly different ways several times, but it's one of these schemes which it might seem extremely obvious, but then one starts to look at it a bit more and then one realizes, okay, there are some trickier things to consider here also. But the overall idea is very nice and practical, so to say. But the actual very nitty-gritty of the technical details can be more involved. Let's say if you would like to set up your own PAW code. Okay, so on the left-hand side, you see the all-electron wave function. And I took this example from a nice presentation by Blöckel. So the originator of the, so who first presented the PAW method. And I recommend having a look at his presentation if you want to have more details about it. Yeah, so on the left-hand side, we see there are two atoms, and these are two chloride atoms, I think, from the example. And on the right-hand side, we see how we can describe these all-electron wave functions. So first, we have a pseudo wave function, and we can see that it's completely smooth over the whole area, both in the interstitial and the augmentation spheres. But what we do is that because it's smooth in the augmentation sphere, we actually need something which better resembles these very localized states there. And what one can do is an expansion over all electron partial waves, which we then just add inside these augmentation spheres. And since we added these ones, we should remove the pseudo parts from the inside of these augmentation spheres. And when we do that, what we have is actually, again, the complete all-electron wave functions. And we will come back to this again and again. So it's an extremely useful relationship here. And I should mention a little bit about so-called transformation theory. And that's how one gets from the, so to say, true all-electron wave functions to these auxiliary pseudo-wave functions, that they are related via this linear transformation operator. And what is extremely useful here is that if we start from our regular equations, so to say, so the Korn-Sham equations, we can rewrite all these equations by just inserting the transformation operator in the proper places. And so it means that if we want to get expectation values, we can evaluate them both directly for the true all-electron wave functions or for the auxiliary pseudo wave functions. So that's the usefulness of this transformation operator. And here a little bit more about it. So I will not go too much into detail, but we can see here that it's a unity in the interstitial, which is outside these augmentation spheres. And inside we have a local transformation operator S. So the interesting things mostly goes inside this augmentation sphere. And inside the sphere, we have the all-electron partial waves, and it's possible to set up a relation between the all-electron partial waves with the pseudo partial waves through this local transformation operator, and it's possible to rewrite this relationship a bit. And finally, also introduce the projector functions, which are important in this scheme, so that the pseudo wave functions are expanded in the pseudo partial waves, and we have this projector function, and we also have some conditions for these projector functions, so that we need to have this delta function, for instance. And if you want to study this in more detail, I recommend to having a look at the papers by Blöckel, and you can also have a look at the typical VASP references. Okay, so from using the previous relations, we can rewrite a bit here. So the local transformation operator, and we get a final expression for it. And then we also see this expression for, on the left-hand side, the all-electron wave function, and on the right-hand side, we see actually 3 different terms. So with the pseudo wave function, which covered the whole space, and the adding of the all-electron partial wave functions and the removing of the partial pseudo wave functions. So we once again, we see exactly this first picture which we started with, that we came to that one. Yes, so we get a final expression for a true all-electron wave function described in this way. And we also see that we have these projector functions here in this equation. And I will just show quite quickly a bit about these different type of partial waves with some examples. So this was for iron. And we can see the all-electron partial waves here, how they behave. So that is the fully drawn lines, and we can see that they have a correct nodal structure. So we have more oscillation inside the augmentation sphere. But when we are looking at the pseudo partial waves, they are much smoother inside. So that are the dotted lines or the hatched lines. Here is just some example of the projector functions, and this is also from Blöckel's presentation, and this was for chloride atoms, and here was an example for projector functions for S-type, P-type, and D-type partial waves. Here is just again the wave functions, once again described in a different way here. Maybe I think we're getting closer to the first break, so I will speed up a little bit. Here is some even more examples. So on the left-hand side, we see the all-electron wave functions, which is the fully drawn, and we see the pseudo wave functions, which are the much more smooth hatched lines. And on the right-hand side, we see their associated projector functions. And here, once again, an example of a PAW augmentation. So first we start with completely the pseudo wave function over the whole space, and then we remove the pseudo part inside the augmentation sphere. So you can see there is just now 0 there, and then to get to the all-electron wave functions, we need to add the partial all-electron waves there. And this PAW augmentation is very useful. So we saw it now for the wave function, but we can also use it for charge density, kinetic energy, exchange correlation energy, and Hartree energy. So it's an extremely useful scheme. And here is just how it looks like for the total energy. So we have these 3 terms. So we have the complete pseudo term, we have the all-electron term from inside the augmentation spheres, and then we remove the pseudo parts from the inside of these augmentation spheres. And what are the approximations we have used so far? Well, I already mentioned that we have a frozen core, so we don't consider the core electrons explicitly. Though the PAW method, it's still an all-electron method, and one can actually put back the core electrons. And here is a reference to a paper by Marsman and Kress, which one can have a look at if one is interested. And we also have an energy cutoff for a plane wave expansion. So that also becomes quite important to consider. And we also have a partial wave expansion. And things to note about the PAW method, well, it's an all-electron method, meaning that the valence states are orthogonal to the core. We use a frozen core approximation, but we could actually reintroduce the core electrons if we want to. So we use plane waves, meaning that we can have very fast calculations using the fast Fourier transforms in the reciprocal space. And forces comes from the total energy expression. And if you're starting your point of view from a PAW method, you could consider that linear augmented plane waves is a special case of PAW, and pseudopotential methods like the ultra-soft pseudopotential methods could be considered to be an approximation of PAW. Little bit about accuracy. And usually for benchmarking, one typically compare with full potential LAPW methods such as V into K. And here is a comparison if one is looking at elemental crystals. So the difference in energy per atoms, comparing VASP between 2K, and one can see it's quite close over the whole periodic table. And here, okay, so sorry, this slide is a bit busy, but this is from a very interesting paper where I compared many different density functional theory codes to see, well, how do they actually compare with each other if you consider equation of state and so on. Because as time goes by, we would expect a kind of convergence of the results using different density functional theory methods, because there is nothing which says that, well, it would be strange if they didn't converge, considering the development of the different codes and also the access to more computational resources. And what one could say is that modern DFT codes should give quite similar results. So I guess that is the gist of this picture. And greener is closer in this case, and redder is more off. But the ones here with red are probably using some very old basis sets. Okay, so I see it's 11, but I think it's just a few slides, so I will just show them, I think. So this workshop is about VASP, but you should know that there are other DFT codes out there using the projector augmented wave method. And typically the importance is to have a good potential database. And if you have a license to VASP, you get access to a quite good database, I should mention. And you also have then other PAW codes such as Ab-init, Quantum Espresso, GPO, and several more. But I guess these other three are probably quite well known, so I think it's good to mention them. Okay, and finally references. So there are quite good presentations. So I really recommend to check the presentations by Marshman and by Blöckel. And here are also some basic references. And if you're looking for a book, you have a one by Martin, the electronic structure book, which is also a recommended read. Okay, and that concludes the first presentation, and I think we take a break here. Yes, so this second presentation will be about the VASP basics, and we heard a little bit about theory, but if you're really interested in the theory, it's good to have a look at the different resources, for instance, at the VASP developers page and the VASP wiki, where you can find links to their presentations and also their YouTube channel, where you can see some presentations, and of course the scientific papers and the book by Martin, for instance. Okay, so this second presentation this morning is about VASP, some basics. Here's just a reminder, it's a VASP Best Practices Workshop. Yeah, so we will talk about the Vienna Ab-initio Simulation Package, so VASP. And we will talk a bit, or I will show a bit where to find the information, because it can be quite useful to see if the cluster where you will run jobs, they might actually have a VASP installation ready for you to use if you have a VASP license. So at the different centers, if we have a center installed VASP, we always have a way to check that a user has a right to use the VASP binaries. And we check this with the so-called VASP portal, when a center can find out the correct permissions. And maybe I could probably mention it already here. So you might know that it was quite a big shift from the older VASP 5 to the newer VASP 6 version. So many groups still might have an older license for the VASP 5. So that means they have a right to, so the members of those licenses, they have a right to use the last patched version of the VASP 5. And that we, for instance, have available at NSC, but also at other centers. But for the newer VASP 6, the licenses looks slightly different. But typically, I think you get a possibility to upgrade the VASP to the next VASP version within 3 years from you bought the VASP 6 license, roughly. So if I want to continue to get fresher updates, so to say, then one needs to renew the license further on a bit. But that one can, of course, discuss with the VASP company. Okay, we will talk about the starting files and some important parameters for the input and output, and I will show you some examples. And the same as for the other presentations, when something is underlined in a presentation, then it's a clickable link in the PDF document, which you can download. So hopefully it can be a bit useful. Okay, short background, and I think I showed a very similar slide already. Yeah, I talked a little bit about the software license. So to use VASP, you need to buy a license from a VASP company in Austria. And nowadays, when you buy a license, it will be for VASP 6, and you get a possibility to update for the next 3 years if it comes a new version. And as I mentioned, so some groups might still have an older VASP 5 license, so then we have all the rights to run VASP 5. We already talked a bit about PAW, and that it was widely used in academia and industry. Yeah, VASP 6 is available since 2020, so it's been out now for some years already. And yeah, some starting advice. So if you are just starting with VASP, I really recommend to read the documentation, run some examples, read the documentation, try to understand the different parameters and what they do. And typically the VASP default settings is usually a very good starting point. So here is some caution. So if you start in a research group, it could be that you inherit some certain input files. And in some cases, it might be good, of course. In other cases, one need to be a bit cautious. So for instance, there might have been some changes in VASP over time. So if these are very old files, maybe the recommended settings or recommended ways how to run certain methods might have changed a bit. And also, if there are lots of things in these files, it can become a bit difficult to read. And what one should know about the input files is also, let's say, if one misspell a parameter, which you write into the main input file, which is incar, then VASP will just ignore it. So you might think that you had a certain setting, but if you misspelled it, VASP actually doesn't use it. So that might be a thing. Or you set the same parameters several times in the incar file, so the main input file of VASP. If you did that, well, I think it takes the last one. But as you can understand, it can become quite difficult to read and understand or overly cluttered input files. Yeah, and considering VASP installations, of course, there will be different versions. And in this workshop, in the hands-on part, we will use the latest version of VASP, which is 6.4.3, if I remember correctly. And at the different centers, we can typically install special versions of VASP. So there are, for instance, there are patches available for VASP to work in a certain way or include different type of approximations. And we at the centers, we can typically help you with such installations. And we also try to document a bit what we are doing. So one of my tasks, for instance, is to help users with more specialized installations on VASP, on Tetralit, for instance. So resources, so I also mentioned this already, but it's quite important, and I really recommend to check the VASP wiki and manual, since it contains so much information. And you have every parameter you can find is documented there, unless there is some maybe new functionality which maybe it's not 100% tested yet. Maybe then, yeah, there might be such corner cases, of course. But then one could, of course, ask the developers about it in the VASP forum. And I mentioned already that there you can find always many different presentations and also YouTube channel from the VASP developers and so on. Yeah, so maybe I'll skip to the next. Okay, so VASP at different HPC centers. So to no big surprise, VASP is installed on Tetralit, so or NAISS system, and Sigma for Linköping University users. But also at other NAISS systems around in Sweden, you can typically find VASP installed, such as Dardel, for instance, at PDC, KTH. And in Umeå at HPC2N, you have the local cluster for Umeå University, so Kebnekaise, where you can also find the VASP installed. And actually, when I was checking the Leonardo, the EuroHPC computer, they seem actually to have a VASP installation. But I thought, well, probably I'll try to make my own installation just for this course. As for me, it's anyway more interesting to try a bit and compile and install and test myself rather than maybe using a center's installation. But of course, I mean, it could be interesting to compare, of course, also. And I could also mention Lumi. It's also a EuroHPC cluster located in Finland, and there you have a nice partition, so for the Swedish research. But on Lumi, they have another policy where I think if you have a VASP license, I think you need to install it yourself in the project area for your group, if I remember correctly. But I assume that they might give you a recipe or tell you the preferred way to make this installation. So that is another strategy from a center side, that one could provide, like, okay, at our center, this is the preferred recipe if you want to install VASP, but we do not handle a center installed version. Okay. And yes, so the latest version of VASP is 6.4.3 from March this year. And one can check what they wrote about it, what the changes were. So usually there can be several bug fixes, for instance. I think there was maybe something related to veneer, maybe in the last update. And also, I would say this machine learning related things tend to move a bit fast also, so to say, with the later VASP updates. Okay, so here's just a list of the different utilities. So you can use VASP together with veneer 90. You have transition state tools for VASP, V-test. You have a solvation models for VASP, VASP zone. You also have Bayesian error estimation functionals. And you can also have tailored binaries if you want to have a constrained structure relaxation. But I will come back to that in more details tomorrow. I will show in the last presentation many different tools which one can use. Okay, so this is just showing the main VASP page, so the official one. And here you can find all these links to the wiki and forum, as I already mentioned. Yeah, here I just show what happens if you click on this Pi for VASP. So this is a relatively new tool. So as you can hear, it's made in Python, so Pi for VASP. So it's a useful tool for doing some quick analysis, for instance, in Jupyter Lab. And I tried to install this on Leonardo, so hopefully it will be possible to check it out in the hands-on sessions after lunch. And it's also available on Tetralit in a new module, which was prepared. And yeah, and I should mention there is an older tool also called P for VASP, so without the Y. Yeah, and that is also very, very useful, though I think Pi for VASP is probably more updated and more supported directly from the VASP developers. But still, this older tool, P for VASP, I still think it's very useful, and it's available on Tetralit, and you get a graphics window where you can have a look at the system, and one can do different type of plots and save to a file in that program. Okay, here I'm just pointing out the VASP wiki and the forum bottoms. And here, VASP manual, so there you can find all these different examples, and most of the examples which we will show today are actually heavily inspired or quite similar to examples which we learned from the VASP wiki, though we changed them a bit so they would be suitable to run more directly on Tetralit and Leonardo. Yeah. Yeah, so there are lots of examples, and also for the hands-on part. So you might remember from a schedule that we have a guided part and a more free open part. And in the guided part, we will show more directly, we go through different examples. And then later in the evening, we have a more free part where you're very welcome, for instance, if you're interested in some other examples and the ones we have prepared, you can have a look at the examples here on the VASP wiki and find if there is someone you would like to have a go at. Yes, so here is just showing the NSC main webpage and where to find information about VASP here. Actually, the quickest way is probably to click on that magnifying glass and type VASP and see after that NSC site Google search what pops up. Then you will probably see this installed Tetralit VASP page. That is maybe the quickest way. So here was just showing clicking around how to get to that page, basically. Yeah, it takes some time, but finally one gets there and where one can read all about or different VASP installations at NSC. And also there can be some more information, for instance, about how to run VASP and so on. And if there is some certain problem with some versions, what to do and so on. Okay. Yeah. Here I also showed how it looks at another center. So for instance, if you're running on Dardal at PDC KTH in Stockholm, you can also have a look on their corresponding VASP pages and what they recommend how to run VASP efficiently on Dardal. Yeah, here is just some example of day-to-day tools which one can use in the pre-processing and post-processing using VASP. And this we will have a look in quite some more detail tomorrow in the final presentation. But I mentioned Pi for VASP was not listed here, but I also mentioned P for VASP. And even if it's an old software, I think it's quite useful and quite good to have. And it's installed on Tetralit at least. And then we have the typical crystal viewers like XQstan and Vesta. And we have, for instance, AESC, which is a collection of many Python scripts and can be very useful for many purposes, and we will see some demonstration of it in the hands-on. And also the interest for regular day-to-day tools can be like using Python, and probably we will use like Python a bit more than the other ones like R, MATLAB, or Octave. At Tetralit, we also have a software suite called Schrödinger, and in that one, it's actually possible to create and view structures also. Though it's maybe a bit more suited for molecules and so on, compared with solids. Okay, so with VASP, there are quite some different types of calculations which we can do. And very common is structure relaxations. And there are different ways how to do that. And as I mentioned before, it's quite common that even if you're using some other software, such as EMTO or Vint2k, so other DFT software, many still use VASP for relaxing the structures. So it's quite well used for that purpose, I'd say. And of course, after relaxing your structure, you might be interested in the total energy of it. So you do just a regular self-consistent run where all the atoms are fixed. And we can do it in the regular fashion with the PBE flavor of a generalized gradient approximation, which is probably the most common exchange correlation functional, both for VASP, but also using other DFT codes. But you can also use hybrid functionals. So the HSE06 is probably the most common one, and where you mix in a bit with exact exchange. But you can also go beyond DFT, so using the GW approximation. And you can do density of states calculations, band structure, have a look at the charge density. You can do molecular dynamics calculations. And now I did not prepare any specific example for MD, but there are several ones if I want to have a look at it. So you could probably have a look at it from the VASP wiki and then change it accordingly, looking at other examples which we prepared for Tetralit and Leonardo, and change that example so you could run it on the supercomputers. One can also run VASP within a special framework. And for instance, V-test I mentioned here, I think it's quite common these days to do calculations for phonons, for instance. So probably some people use like Phonopy and so on, I guess. Okay, and at the VASP wiki we find many examples and tutorials for these different types of calculations. Okay, so where do we start now if we want to do VASP calculations? Well, we have a main input file, and that is the so-called incar, where we put the input parameters. And as I mentioned, if one spell a parameter wrong, VASP will typically just jump over it, so it will not crash or tell you that the parameter isn't acceptable or anything. It works in the way that it takes what it can read, and then it tries to run that calculation. So one has to watch out a bit here that one didn't make some mistakes. And also there is no special order needed inside the incar. I guess probably at the top, I think it should be a comment line or something. So maybe that's an exception. But we could have a look at it later on. So incar is the main file for the input parameters. And then we have a structure, and that's in the postcar file. And we will have a closer look on it. And this we can typically generate with some codes. For instance, if you have a file in the CIF format, so you can get it at the Open Crystallography database. you have lots of values input there from different experiments. If you have such a CIF file, you can use programs such as SIF2Cell, and you can convert it directly to a postcard. So that's quite convenient, I think. And I think I also installed SIF2Cell on Leonardo if I want to have a look at it, and it's available on Tetralit. Okay, and then we have potential files or the POTCAR. And if you remember from the previous presentation, I mentioned that the potential database is quite important. So then you select some DFT software for the PAW. You really want to have a good potential database for it, because to create potentials yourself, it's a kind of both a science and an art, so to say. And if one is not expert in it, one should probably, leave it to the people who are really working with this. But it is a good database of potentials available with the VASP. And I should mention that with the latest VASP version, so 6.4.3, there was also an update of the potential database. So we will use that one for the workshop. Though, of course, not all elements were updated, but the updates are usually, if one really found a reason to update the potential file. Okay, and apart from these three files, we also have a file where we put the K-mesh. So it can be a mesh, or one can actually just put a list of K points. And it's also here that one would put the list if one want to compute a band structure. And I should also mention that it's instead of providing a K-points file, it's possible to use some parameters related to, you can set a density of K-points, and then VASP will figure out what mesh that corresponds to, and it will use that mesh for you in the calculations. Because sometimes maybe you have a better idea about what the density would be, rather than trying to figure out exactly how your K-mesh would look like, because the K-mesh, there you have to consider how your cell looks like in a reciprocal space. And in most cases, it's relatively easy because it's just inverse of the real space. And in particular, if you have a cubic system, it's very easy, because then both X, Y, and Z, they will be the same. But we will come back to that. Okay, and apart from these input files, you will also typically have a job script, unless you're running your job interactively, which is possible to do on Tetralit for sure. I think one can run interactively on Leonardo probably, though I didn't try it. But for the workshop part today, I prepare job scripts which can be used to directly submit to the Leonardo or to Tetralit, so for the workshop projects. And both at Leonardo and at Tetralit, and also at the different NAISS clusters around Sweden, we use this Slurm batch queue system, and it's quite a popular choice among the different supercomputers around the world. Okay, a bit about in-car parameters. Most important is maybe the precision one, because it will set your energy cutoff for the plane waves, and also how to handle your fast Fourier transform grids. But we also see that NCAT, we have it explicitly here, and that is recommended by the VASP developers. So actually, if you don't set NCAT, VASP will figure it out by looking into the PAW file, and it will use the default value for your element. And if you have several elements, I think it will take the highest default value. So your calculation will still work. But if you go back to this calculation in the future, I think it's a very good convention to always explicitly set the NCAT in your in-car file, so it's always there, so one can always very quickly check what the value used was. So that's a good convention. Then we have the algo parameter for the wave function optimization. And usually I think the normal one is probably the default choice here. So it's possible to use also faster algorithms for the calculation. It depends a bit on what you want to calculate, how much effort to go through to consider to use different algorithms. So maybe we will come back to it tomorrow. Yeah, tomorrow I think I will show you an example what happens if you choose different types of algorithms here for a wave function optimization. And we remember it was this step when we had this iterative cycle, it was this step in between when we were doing this total energy minimization. Okay, another very important parameter is number of bands. And if it is not set, it will be determined automatically by VASP. And it might depend on how you run your job, exactly how it will set the number of bands. So here one should watch out a bit, especially if you run your job in slightly different ways, like on different number of nodes, on different number of cores, using GPU or not. This value might change. And it might actually slightly affect your total energies. So even if the uppermost bands will be empty states above the Fermi level, you can still have an effect of a total energy. So here one need to think a bit and watch out. And also one should remember that for certain methods, such as the GW, you typically need many more unoccupied states. So then I think that the VASP default would probably give you too few number of bands, for instance. So there are some things to watch out for here when considering the number of electrons, the number of bands to include in your calculation. And then we have some parallelization parameters, NSIM, NCORE, MPAR, KPAR, and I will come back to them more tomorrow. Yeah, so they are more for considering when we run VASP in parallel. And the first four here I mentioned was more related to the accuracy and method. And it's recommended to set the energy cutoff for the plane waves, and it's related to the completeness of the basis set. So how many plane waves are used to describe your system? And we will get back to this in lecture tomorrow morning. Yes, and typically the default parameters in VASP are quite good. And so if you don't set these parameters, you will get a default from VASP. But as we remember, they really recommended that you set this NCAT, so for the cutoff energy of the plane waves, so how many plane waves we will include basically for doing the calculation. And also, especially considering forces, we might want to set precision equal to accurate to have a bit more accurate calculations. And algo, we will come back to it with some example tomorrow. Default is a normal, but one can also have these fast and very fast options also. It can depend on your system a bit, what is actually best to use. It's not always, doesn't always work to use this very fast, for instance. And the number of bands, one should also watch out, even if you set it explicitly, it could be overridden by VASP for some reason. Maybe depending on exactly how many nodes and cores you're running on. So the best is to watch out, in particular if you're looking at properties related to the total energy. And I mean, if you're interested in density of states, I mean, then it's mostly interested, okay, do you want to see the density of states far above the Fermi level? So then, of course, it becomes interesting also that you need to add more empty states if you want to see them in your plot. Okay, and then is just again the different parallelization parameters, and I will come back to them tomorrow. Yeah, so here, just in very brief, and you can refer to a VASP wiki for more details. So here I just put out the different defaults, which will be used by VASP if you set nothing. And if you have a presentation, so you can see all parameters are underlined. So if you click on them, you will go to the corresponding VASP wiki page where you can read more about them. And let's see, yeah. Let's see if there is someone we should discuss a bit more about. Some of them we will come back to in the examples. Yeah. Okay. I could mention we see this NELM, N-E-L-M parameter, so max electronic self-consistency steps. So that's when we are running these iterative cycles, when the default is set to 60 of them for the electronic part. And that means that when 60 have been done, then VASP stops. And it will stop even if it is not converged. I think with VASP 6, maybe now there is some warning which tells you that it didn't converge. Maybe that is changed now in VASP 6. I actually have to check, because with the VASP 6, several more warnings were introduced. But with VASP 5, so the old VASP, if it doesn't converge, it will actually not say anything. So you have to check each of these iterative steps and see, did the calculation actually converge at the end? So that is important. Yeah, and we have other parameters here, but we will come back to them in the examples. For instance, how to treat a partial electron occupancy. That typically, if you have a band gap system or a metal, you have different choices how to set this, and it's about how you smear the electrons at the Fermi level. And if you want to do very accurate total energy calculations, you should set this to -5 in order to get the tetrahedron method. And you typically also want that for density of state calculations, but that choice is not suitable if you're sensitive to, if you're interested, for instance, to get accurate forces, then you need to set this smearing differently. But typically the default value from VASP will be quite good. Okay, so I see we're getting closer to 12, but I will speed up a little bit. So here is an example of a postcard file, so the structure file of VASP. Here, it's a simple example for FCC nickel. So we can see that the first line is hopefully some useful comment what this is. The next line will be the lattice constant, or if it's a negative value, it will instead be the cell volume for this structure. Then it's followed by the three lattice vectors. And then I recommend that one should always put the elemental symbol here, because I think a new default, if you create a postcard usually from some other program, is that they do not put it here, but they rely that you have a correct order of elements in your postcard file instead. But if you want to see the structure, for instance, using Vesta or some other tool for looking at crystals, you really would like to put the elemental symbols here so that the software will plot it correctly. And it's also a good reminder to you what your structure looks like, of course. And you can have both Cartesian or direct coordinates here. Here I'm showing a slightly more complex example. So this is from one of my old calculations for, seems to be silicene on a silver surface, and hydrogen here also. And here note the order of atoms, the hydrogen, the silicon, and the silver. So the 14 first positions here at the end will be the hydrogen atoms, which will then be followed by the 14 silicon and then the 108 silver atoms. And in this example, I'm also showing this selective dynamics for the structure relaxation, that depending on the coordinate, so you can fix or allow a position to relax for the X, Y, and Z direction. So that is also very useful, and we will see that in some of the example after lunch. Yeah, so I mentioned crystallography open database, very useful, and for general crystallographic tools, one can have a look at the Bilbao crystallographic server. You can, for instance, look at Brillouin zones, and there are many things there. Here about structure files. Vesta is very nice for looking at structures, and you can also handle structures using the ASE or atomic simulation environment. I mentioned SIF2CEL already. P for VASP is quite nice. As I mentioned, it was installed on Tetralit, and I will talk a bit more about different tools, and we will see some tools also in the hands-on session. Okay, a little bit about the potential files, so the PAW potentials. So this we typically get from the database, which or potential which comes together with the VASP license. And this is not files which we edit so much, but if you look at the top of them, you can find some interesting information, the type, element of the date it was constructed, atomic configuration, energy cutoffs, and so on. And a little bit more about these potential files. At the VASP Wiki, you can check your recommendations, how to choose them, because typically for an element, you can have several of these POTCAR files. And the reason is, for instance, you're interested in some high pressure, then you might want to have a different type of potential file. And nowadays, you also have the so-called GW potential files also. And I think the VASP developers, they say that these are actually, in general, quite useful, even outside GW. And in particular, one should mention, if you have short bonds, you should use the ones with _H. For instance, if you consider, let's say, if it's you have an oxygen and hydrogen, so OH group, or oxygen molecule, so whenever you have shorter bonds, you would like to use these more specialized potentials for that. And these ones will typically also have a higher energy cutoffs for the plane waves. And if you grep for NMAX for the POTCAR, you will also find what is recommended. Little bit about K points. This is again just a simple case FCC nickel. Here we can see that for the popular PAW-method, it's usually best to have odd K meshes because it will guarantee that the gamma point, so the centered point in the reciprocal space, will be included. And there is also an optional shift of this K mesh. I think it might be easier to use the gamma method instead. So then you will always have the gamma point included by default. And this becomes more important, for instance, if you have hexagonal type structures, you need to watch out a bit where this gamma point is, because typically you want to include it in, well, depending a bit on your type of calculation also. Yeah, here is just another example. This is for the band structure, and we will come back to it. This is usually done as a second step, and we will see some example on it in the afternoon. Yeah, here's a bit more. And I see we are soon running out of time, so let me just check how many slides we got. We have a little bit about K-points, VASP binaries. Yeah, okay, mostly some examples. Okay, if you forgive me, probably I can briefly say something more, but I shouldn't spend too much more time, so I might come back to it in the beginning of a hands-on session also, because it will connect to some of the examples which we will use. So typically for a metal, you need to include many K-points compared with materials where you have band gap, where you can just have fewer of them. And the same thing when if we have few atoms, we typically need more K-points. But if we have big supercells with hundreds or thousands of atoms, we need quite fewer or just a single K-point. And one can think of it like if you have a big cell in real space, and then we transform to the K-space or reciprocal space, in that space, you have a much smaller cell, so then you don't need so many K-points to describe your wave functions, for instance. So that is one way to think about it. And one should have in mind that there is no guarantee for convergence. So yeah, we need to check that it works. And I mentioned already about these methods that we have a Moncrief-Pack, but we can also choose the gamma method in VASP. And when we go from the real to the reciprocal space, we have this inverse relationship between them. Yeah, okay, but maybe let's see here. So since it's already 12, maybe I should stop here. It's just some few things, but I could just mention them, I think, in the start of the hands-on session. What do you think, Jonglei? Maybe that's best.
Yeah, we can stop here to take lunch, and after that we can, if it did not take too much time, maybe we can continue this part and give a short.
Yeah, I think it will just be a few minutes in the start of the hands-on, and I think it also connects well with what we will look at in the hands-on session. So
Yes. Yeah.
yes, so I think I stopped with the K points. So we had a quick look, considerations here. Then just a few slides left. So about the different VASP binaries. So when you compile VASP, you will get a few different type of binaries. And the regular version is the one called VASP underscore standard. That's the regular version, which you typically use. But you also have special versions for if you're just doing a gamma point calculation. So if, let's say, you have a big supercell or big structure with many, many atoms, so you only want to run a single K point, then it can be useful to choose the VASP underscore gamma binary instead. And of course, you could have used the regular version, but the gamma point version is more optimized just for a single K point, so that will run faster. So you will save some computational time. And then there is a last version also for non-collinear magnetism. So meaning if you have magnetic moments which are pointing, which could point in any direction, then you should use that particular binary. And if you compile VASP for GPU, so for a newer OpenACC version, you will get the same three binaries with these same three names. And previously there was also a CUDA version for VASP, so for running on GPU. But that branch, I think, is not updated anymore. So what is actively updated is the OpenACC GPU branch, which works well, for instance, running on NVIDIA GPUs. And of course, in some cases, there can be specially modified binaries. And at the centers, we typically can help you with such an installation. If there is a special patch for different functionalities, we could help with that. Okay, so here was just a simple job script. And for the exercises in the hands-on session, you will find some more suitable examples which can be used directly for trying out the exercises on Tetralit or Leonardo. So this is just a simple showing how it might look like on Tetralit. And here we see we are running quite old VASP installations of 544. At NSC, we have a special launcher for MPI binaries, which is called MPP run. And at NSC also, you typically only need to load the particular software which you're interested in. So at NSC, you don't need to load the different dependencies and such. But it's quite common, depending on center, that you explicitly load the different dependencies, and that you will see an example of if you're running on Leonardo. Okay, and here is just mentioning that on Tetralit, some common ways to save memory might be to reduce the number of tasks per node, so 32 cores. So if you only run on half of them, you can save the memory. So if you set the n task per node equals to 16, and on Tetralit you also have a petition for so-called fat memory nodes, which have a bit more memory than the regular ones, but they are quite fewer, so it might take longer to get hold of them in the queue. It's just a similar job script for Dardel at PDC KTH. Though note, this example might be quite outdated already. So one should check on the corresponding PDC pages about the best way to run VASP there. And here you can see it was started using SRun. So a bit similar to Leonardo, as you can see in the example job scripts for Leonardo. Okay, a little bit about output files. So after you have run VASP, you will see that you get some files produced during the run. One file is from the queue, from the Slurm queue manager, and that is typically called Slurm a job ID number .out. And this is basically your standard out from running VASP, what you would get on the terminal if you would run your job interactively. But you get it in this Slurm output file. Typically, it's a summary of how it goes over the iterative steps. Here you might also see some interesting warnings. So it can be good to have a look at this file. But the main output file from the VASP program itself is outcar. This is the main detailed output file from VASP. For a quick summary of the iterative steps, one can have a look at OSSICAR, and we will see some example. And if you are relaxing your structure, you will also see a CONTCAR file at the finish. So after your structure relaxation has finished, you will find your new structure in the CONTCAR file. And for instance, if you want to use that structure in the next study, you copy that CONTCAR file to a POSCAR file in another folder. And if you're interested of checking what happened with the structure at each step, you can look at this xstat.car, for instance. Yeah. And some more files. So this is just a brief. So there are many other files, but these are maybe the most important ones. You also have DOSCAR, total partial density of states, the CHARGECAR for charge density, and you have a WAVECAR for the plane wave coefficients. And both WAVECAR and CHARGECAR can be useful for some restarts. I think most useful is maybe CHARGECAR to use for restarts. if I would just make a general statement. Okay, so here is a quick look at the OSSICAR. So you can see here that it's showing each iterative step, and we can see the total free energy here. And we also see the energy difference. Typically from some criteria, we want this energy difference between the steps to become smaller and smaller as we do this minimization of the total energy. And we can see here that it seems to have converged at the 10th iterative step. And we can also, there are some more things here which can be interesting. So charge density, residual vectors. So yeah, so these parameters should also become closer to 0. And at least in VASP 5, we really needed to make sure that the convergence had been reached. I think in VASP 6 that might have been added, that there is a warning now. Okay, and here is the corresponding Slurm output file, which might look like this for the same run. And you can see here that in the top, we got some information from VASP, how it's running. So that can be useful sometimes to really make sure that you're running on the hardware, which is what was intended for. For instance, if you're running on GPUs, you would like to see if it's running on 1 GPU, 2 GPUs, or so on, just to make sure that everything's working okay. So here in the standard output, in the Slurm output file, one would typically check for different warnings. And one might see several type of warnings. But at first they might look a bit dangerous, but many warnings should really be taken more as reminders and checking that you're actually doing what you want to do. So if you see a warning, for sure, read through it, and then you will understand, or you should think, does this apply to my case? Should I really do something? Because some warnings you will for sure see quite many times, but it really depends on what you're after, if you should really change something. Yeah. Okay, and here was just a little bit about the VASP 6. So I think here was a link to different features. And what is new is in VASP 6 is that you have hybrid OpenMP, so you have OpenMP threading, but also MPI parallelization. And I think I will show some examples tomorrow where it can be useful. In particular, it's useful when you want to save a memory. So when the RAM is a factor for your job. One idea can be to reduce the number of MPI ranks and increase the threading, and in such a way save total memory. And I already mentioned that there is a GPU version, so built on OpenACC. You have random phase approximation and GW approximation with cubic scaling. Electron-phonon coupling using stochastic displacements of atoms. You have a machine learning force field for molecular dynamics. And with some of the newer updates of VASP, the speed up was quite large. So one could notice that. Okay, and that was the presentation for today, and tomorrow we will look much more into running and performance, parallelization, efficient settings, problems, and in the final presentation we will have a look at different kind of tools, so utilities, and we make a final summary of the presentation part. Okay, so that was now finished. And we can go to the hands-on part. So for the hands-on session, you can find all the material here. You can also find the presentations. So the first and second one now are updated, and the third and fourth one I will put there later on. But for the third and the fourth one, it should be quite similar to last year's workshop, if one already today wants to have a look. And I put here, so depending if you will be working on Tetralit or Leonardo, I put a bit different starting descriptions. So with Tetralit, so if you're a NAISS user and you have an account on Tetralit, so I've added you to the VASP workshop project, and hopefully it worked well. And here on this page, you will have a quick guide for using Tetralit. So if you follow that link, you come to a page with some information about this project. And note here that we have a special reservation for today for running on Tetralit. And if you want to use that special reservation, you can, in a terminal via Finlink, for instance, you can type this use reservation, VASP workshop, and these numbers here. So please have a look on this page. And that should give you quick access to I think we have 5 nodes which were reserved for this workshop on Tetralit. But these examples are quite small. So I think if you look at the job scripts, I typically run on 4 cores or 8 cores. So I think 5 nodes in total should be plenty for the exercises. Yeah. So I guess that's the most information about that. Yeah, I should also mention that I think some of you who are NAISS users who will work on Tetralit, you probably have a VASP license already. But just to be sure, I also put you in a temporary VASP license group. So you should have access to the latest version of VASP, so 6.4.3, which I thought would be most interesting to use in this workshop. Otherwise, please send us a message or put in this HackMDE page for the session. Yeah. Okay, so that was a little bit about using Tetralit. And then we have information for using Leonardo. And I think accounts and such, I assume that most people probably got set up with it already yesterday, but we will see. I mean, I assume some questions might pop up, but we will see. And I assume probably in the EMTO workshop yesterday, you probably got a bit familiar with Leonardo. But anyway, so I put some information here, for instance, about example job script. And also all these scripts will be available in the examples, which you copy from a certain place in the project area. What one can notice here, so thinking back to the last presentation, I showed that at NSC you only needed to load VASP, and then you automatically would have all the dependencies already there. On Leonardo, we need to be a little bit more careful. What I did here was to create some modules just for the workshop. So you will have 2 VASP modules, so one for CPU and one for GPU. And you will have a module, I think, for SIFT to cell, and you will have a general Python module and so on. And I also tried to describe these different software. Yeah, so it can be useful to have a look here. Yes, and we should not forget the useful tools page. Here I tried to make a general description of each tool, and you can see you can click on the Tetralit button or Leonardo button, and you will see what information you got there. I thought I put the more basic stuff here also about typical commands, text editors, tmarks, GNU-plot, and so on. But also about P4VASP. So we can see that P4VASP is available on Tetralit, and unfortunately we don't have it on Leonardo. But Pi for VASP we have on both systems. And here is some general descriptions, how to use Pi for VASP, and also in the examples it will be described how to use it. And the typical use of Pi for VASP is that you use it via Jupyter Lab. So you start this kind of notebook and you run the code directly, the Pi for VASP. And I also tried to describe how to do that with further down this page when one comes to the Jupyter part. But yeah, so here it's shown on Tetralit, we have a Pi for VASP module. And on Leonardo, you first type this module use and this long path, and then you get some workshop modules available, including this, what I call Python VS, ENV, and so on. Okay, also the atomic simulation environment is available on both Tetralit and Leonardo. Here, because first I wasn't sure if we would get Pi for VASP to work properly on Leonardo, so I thought we could also have a look at VASPKit, which is a quite nice tool, which can be used both for pre-processing and post-processing. So I set it up on Leonardo, and here's some description how to do if you want to try it out. And it's quite useful to follow its link where you can read a bit more about it. But if you quickly, for instance, want some information about or put out the density of states and band structure and so on, it's possible to use that one. And on Tetralit, well, I can tell you how to install it, but I didn't prepare anything right now, but it should be easy to set up if someone is interested. Also Sift2Cell, available on both Tetralit and Leonardo. I kind of like it because I use this open crystallography database a lot. So then you have all these CIF formatted files, and with Sift2Cell it's very easy to just save it into many different formats, and VASP is one of those. And I think you also have some further functionality in Sift2Cell. Perhaps you can also build a supercell directly with it. I forgot, but it has some extra functionalities. And I think Vesta is a very nice crystal structure viewer. And it should be very easy to install on your local computer, just to download and click install, basically. So that I could recommend to try out if you aren't using it already. And on Tetralit, it's available as a module. Yeah, okay. And finally, it's some information about Jupyter Notebook and Jupyter Lab. And on Tetralit, you could load the Pi for VASP module. Then you have access to Jupyter Lab. And if you're logged in via FinLink and you have a terminal, so you could start a session directly in the browser so that you get access to Pi for VASP. Though one should note that typically, I mean, the login node is not always the best place to run stuff, depending on how heavy it is. If one is just doing some simple plots for VASP, using Pi for VASP, I think it's not so heavy. But sometimes one needs to be careful, and then one alternative is to start an interactive job on Tetralit, and then one can start Jupyter Lab. One can use this no browser option and this IP flag with the node name and start it. And Leonardo, I also tried to set up some descriptions, how you could use it here. And in this case, you would have to set up some port forwarding for it to work. Yeah, so we'll see. So it depends a bit. Yeah, if it takes too much time to get it to work, then I would suggest to maybe not spend too much time on it, but concentrate on the other parts on the workshop. For instance, even without setting up the Jupyter Lab, it will be possible to plot static images using both Py4VASP or GNU-plot and so on. So while it would be nice to have it up and running, I would say don't spend too much time on it. And also for me, it took quite some time to get it to work. So yeah, so it depends, but yeah, it can be useful to have a look at least. Okay, so this was a basic description of the different tools which were directly available, and of course there are many other which I don't mention explicitly here. And as I said on Leonardo, we prepared some modules just for this workshop. And yeah, and you can see here that we have a list of different hands-on examples. And this first part of the hands-on session, I thought I can show something. So I could start with the first example, maybe on Leonardo and Tetralit, and just go through it and explain what we see and what we can do. So that's intended for this more guided first part. And if you have questions, you're very welcome to put them in this. I think there is a link somewhere to this so-called what is it called? The special page we have for today, where one can note these things down. And also I, and probably mostly the helpers, we will have a look on this page and what questions pops up. And I think for the general questions, we could just have in this more open forum. Discuss about them. Yes, sorry, was question? Okay, maybe it was just the mic. Yeah. Okay, but yeah, before starting, I should also, I should just mention a bit more about examples. So you can see here, so it's a list of examples. You can click on this FCC Silicon, which is the first one. And typically we based them on a corresponding VASP example, but it's a bit tailored more for the particular systems which we use, like Tetralit or and they should be quite self-contained, so that can just start at the top and just follow all the instructions until the end. And sometimes there are some questions or thoughts, or it says, okay, you need to think a bit about so on. But it should be quite self-contained. But since this is the guided part of the hands-on session, I will go through each and every step. And probably I will also remark on other VASP-related stuff, which might be good to think about by going through these examples. And as you can see, it's just to click between Tetralit or Leonardo, depending on where you are working. So basically, in the first part, we will go through these ones. And also notice where it's important not to forget this more examples and topics, because I think depending on what you're doing, so I mean, some of you might already be a bit familiar with VASP and you have used it for some time. So maybe it doesn't make sense to start with the most simple or example, which for you is a bit trivial if you already have some knowledge of VASP. So an idea is that if you're looking into a VASP wiki at the examples and tutorial, you have a quite large collection of examples which you could choose. So for instance, if you're interested in molecular dynamics, you can have a look at that example from the VASP wiki. And by using some of the modified examples which we show, you could yourself modify that VASP wiki example, so you could run it, and we could also help with that a bit. So there are quite many things to have a look at. So I don't think there is any risk, so to say, of having nothing to do. So there should be many things which one could consider here. And I also suggest that, for instance, you might be interested in some own material or just want to try out something. So you could go to the crystallography open database, for instance, and you can search for some certain structure, maybe, I don't know, silver, one element, and just see what pops up. So there should be lots of experimental data. So one could download this crystallographic file. Yes, so here we see several ones for silver. And so it's possible to download and have a look at. And for instance, use a SIF to cell in order to transform it to a postcard file. You can also try out all these different tools for VASP and come back to us with questions, perhaps. And since Leonardo, I mean, it's a EuroHPC cluster which has this quite modern NVIDIA GPUs. So you might be interested in trying out to run some examples on a GPU also, and you could compare it with running on the CPU. So I prepared a module on Leonardo for running the GPU VASP binary. And this job script here shows you how to run on a single GPU. And I would suggest, one GPU is probably enough. I think we need to probably, for the project, we have some limitation how many hours we can run up, so to say. So we will see. Hopefully there should still be some hours left from yesterday's sessions, so one can continue to run a bit. But typically in these examples, we don't consider so much to run production jobs. So this is more like trying out, testing a bit, see what works. So this is more about the principles rather than running real production jobs, because for that we don't have that much core hours or GPU hours to use. Okay. I also had an idea one could do some small efficiency benchmarking test. For instance, you could look at the scaling behavior if you run on a full node, 32 cores. So here, Tetralit and Leonardo is a bit similar because each node has 32 cores, but on Leonardo, it's a single CPU with 32 cores, and it's a very modern Intel CPU. On Tetralit, it's an older one from 2018, and it's actually two CPUs with 16 cores each, which make each node has 32 cores. So in that sense, it's a bit similar between Leonardo and Tetralit. Okay, so this was just some suggestions. And so I don't know if if my fellow helpers, if they have some extra comments. Or we could just start also.
Yeah, I mean, no additional
no.
comments at this point. I just pasted some info on Dardel if someone is really keen, but I think most people will be using either Tetralith or the Leonardo booster.
Yeah. And of course, I mean, sometimes people have access to other clusters, and it should be possible to adjust the examples a bit. So depending on the cluster where you want to run. And these examples, they are made to that you should be able to run them quite fast. Okay, yeah, but then I probably should start with some example. So we could start with the FCC silicon. And I'm thinking the best is probably if I share the terminal screen, I think. So I will stop sharing this one. Okay, so this looks fine, right? Yeah, so I thought since this is still the guided part of hands-on, so I thought just stepping through the different steps. So you remember we have them on the VASP workshop page. So I will put it up here on a different screen so I can read my own instructions, hopefully. Just a sec. I think I put that window somewhere else. Ah, okay, here it is. Yeah, so it's basically made so one can follow each step here. So this is a first introductory example for working with VASP. And I'm clicking here for the Leonardo examples. So I will follow the Leonardo instructions. First is just copy these files, what we have here. Maybe I'll create a new folder, maybe hands-on one. And so I should just copy. Yeah, and here we can see that we got some files, and we recognize that we have some input files here for VASP. And the most important one is in-car. We have a file with K-mesh, the K-points file, and we have the postcar structure file. And then we have some help scripts and job scripts, which we will have a look at. And also we need the potential files. And here it's shown that we copy it. Yeah. And we have a potcar, which looks like this. And one should also show another way to handle this potcar, which is particularly useful when you have several elements, because then you need to put all the potcars in the same potcar file, so to say. Then you would do something like this, that you use the cat command. And see, here we also have a potcar file, but we got it from using cat. And cat is just listing the contents of a file. So if we use it with in-car, we will see the contents of the in-car file. And so we can look here. So in the silicon, FCC silicon postcar file, we can see it's a single silicon atom here. But let's say if we had two separate silicon atoms, we would typically do this twice. So now we actually have two instances of silicon in this potential file. And if we run grep after PAW, we can see them here. You can see the titles PAW, PBE. Yeah, maybe one can, grep like this. Title, I guess, yeah, title, I assume. Yeah, so we see that now there are two in that potential file. But for this example, we will really just need one. So we can, well, and so on, of course. I mean, one can continue. You could even put nickel or any of these potential files which were needed. And now we see, yeah, we have 3 silicon and 1 nickel. So this is a quick way of working with these potential files. And now we have 1, as it should be. Okay. Yeah, so in the example, there are some comments about it. Yeah, if we were looking into a postcard, look like this. We can see the lattice constant for FCC silicon was 3.9 ångström. And I mentioned already before that these lines which said silicon, it's actually not really needed for running, I think, because VASP will find the proper elements from a bot car. But if you want to visualize your structures, and also you would like to quickly see, I mean, what atoms do you really got and in what order in your postcard file, then it's really useful to have all the elements explicitly written out in the postcard file. But notice that in some structural programs, they might use the other format where they don't put out that. So for instance, if you use SIF to cell, you would have to put it in by hand. But SIF to cell would tell you in the first comment line in what order it put the different elements. And yeah, as you can see here, the first line in the postcard file is a comment line. And here it's quite useful because it says FCC silicon, but it's basically just a comment, so it could say anything there. But the best is, of course, to put something useful there. Yeah, we already had a quick look at the postcard. Maybe, or I mean, the postcard. Yeah, we talking about it in the last presentation also. So here you can, for instance, see some information how it was constructed and which electrons are available in the valence, because we remember that in VASP by default we have a frozen core. Approximately we don't have the core electrons. Yeah. And we can have a look at the in-car file. So this is our main input file for doing a VASP calculation. And let's see what we could mention here. So you can see an in-car file can be quite minimal. And we could even reduce it further if we wanted, but many options are also default options, so you would get them anyway. But sometimes, just to be clear, we want to make them a bit more explicit, or if we want to change some option. And here you can see we specifically set a certain energy cutoff. So NCAT 240 electron volts, and one can compare this if we look if we grep into the POTCAR file, we have an NMAX. So typically one would, it's quite common that one set these values around this NMAX value. So here we see it's 245 electron volts for the plane wave cutoffs. And we also see a minimal value which one shouldn't go below. And of course, I mean, this is a quite fast and simple example. So even if we would increase this value quite much, it would still not be very difficult for, I mean, a calculation would take a couple of seconds on a modern CPU. I could mention here, so typically if we increase NMAX, we could start from this value 245, and let's say if we increase it 1.5 times, so if it's 245, you see, yeah, so maybe if we want to have some better, some higher energy cutoff here to expanding the basis, we could use a value, let's say 370, 400 or something like that, if we're interested in silicon, and it will probably be quite well. And if we remember from a lecture, there were quite many, there could be optional POTCAR files. For instance, I said that we have this one with underscore H, if you have short bonds, for instance, and you have the newer ones which are suitable for GW calculations. But it's in the GW calculation POTCARs, they are also quite recommended by the VASP developers, so they could be useful also for many other cases. I thought, let us just have a quick look here. So we can see that for silicon we had two other versions of the potential file, and both of them are actually for GW. And also this potential library is a new one. It was released just now with the latest VASP 6.4.3 now in March. So there were some changes. If we want to, we could have a look if, let's see, so there is a file here which describes these changes. Let's see, maybe README updates, maybe. We could have a quick look. Yeah, okay, so here we see quite some old updates, March 2002 release. So I'm just going to the end here. Here we can see the newer updates. Yeah, for instance, we see in 2022 Terbium, and also for the underscore H when you have shorter bonding and so on. And also, I think this information one typically finds at the VASP wiki also, where they will also say something about it. And I should mention that if you check the VASP wiki, one can actually find the recommendations. So if you are in bit doubt about, okay, what potential files to use, which POTCARs to use, you can find the recommendation in the VASP wiki. So I think I will probably not switch what I show, but maybe I can show the link here. So just a second. So there is a certain page which recommends different potential files. Yeah, I think I found it. It's called Available PAW Potentials. So maybe let's see here. So just a second. Yeah, so I put it in the chat. Here one can read about all these different types of potential files and how to select them. And if I quickly have a look at this page, and let's try to find silicon. Actually, I can see that they recommend, oops, let me see. We had the two choices for the GW1, and one of those were recommended. But I'm trying to find the regular potential file also. Okay, but in that case, we only had one of them, so then it's more obvious which one is recommended. Okay, yeah. Okay, but that was a little bit about potential files. Yeah, if we go back to the in-car, you can see here that the I-smear, it determines the partial occupancies of each orbital, and for bandgap systems, such as silicon in this case. So we could use this tetrahedron method with the Blöckel correction or the Gaussian smearing. And I-smear is the option how to control this. And as I also mentioned during the presentation, that the tetrahedron method, you typically use that one when you want to have very accurate total energy calculations, or you're computing density of states. If you are doing structure relaxation, you don't want to have it, and VASP will also produce a warning for you to remind you if you really want to have that setting. Okay, a little bit about the K points. Yeah, we can see that in this example, the Monkhorst pack is used, 11 by 11 by 11. Well, it's a face-centered cubic system, so it's not so strange. And typically, instead of Monkhorst pack, one could use the gamma mesh instead. In that case, you would always be sure that you actually keep the gamma point, so the 0 point in the reciprocal space, that it's a part of your K mesh. And in particular, concern if you have hexagonal type of structures. Yeah, so what more can be interesting here to mention? Yeah, apart from, as we saw with a pot car, apart from using this cat command and copying it, typically one will not edit it. Maybe, actually, there might be some very special cases when they are edited, but in 99% of the typical VASP usage, one do not edit these pot cars by hand, so to say. Unless you're working with the virtual crystal approximation, if I remember correctly. So, yeah. Okay, but now I'm thinking we're finally getting closer to the step for the calculation. And here, I just suggested that one creates a new directory. And here I said, okay, move these files, in-car, post-car, K points, pot-car, and run to this new folder. And also copy it. So we want to have like this. Yeah. And submit the job script to the queue. Well, first I should go to this one. Yeah, we can have a quick look at the job script also. Yeah, so we can see here that we are working with the correct project account. So this TD, as you see, this S batch -A. We are using the boost. You see this. So I chose a higher priority queue, which is possible to use if one has shorter job. I think the maximum wall time is half an hour, but this, and here you can see in the job script, I put 15 minutes, but that's actually a bit much. One could reduce it if one like. I think the jobs typically maximum takes a couple of minutes probably, but one can let it be for now. And here we also see -N8, so that means we want to run on 8 cores on one Leonardo node. So that is a fourth of the Leonardo regular node, since a node has 32 cores, similar to Tetralit, by the way. Okay, and you can see here that we want to use our specially created modules. Maybe I can show you. And since I created these modules, one needs to use this command module use. And if you do module avail, we should see our course modules in the top here. So you can see we have a SIF to cell, we have a Python workshop environment, we have a VASP 643 CPU version and a GPU version. And on Leonardo, I also installed this VASP kit software if someone wants to try. And the rest is the internal Leonardo modules, which there are many of also. And actually, somewhere there should be a VASP module from Leonardo, but we do not. I have not asked permission to use it, so we can unfortunately not benchmark and see for module faster than theirs. But it would be interesting as a test, maybe. Okay. But yeah, so we can try to submit it. And because I'm in the project group, I will just, so you should not do this change, but I can do this change, I think. Okay. SQ. Let's see if it's running. Maybe it's so fast that, yeah, it's already done. So I was too slow in checking for it. And we had some output here. We can see the Slurm file here. And at the top, we have some information. It wrote, for instance, that we were loading certain modules which we needed to run with VASP. And we have 8 MPI racks, which seems reasonable since we submitted it on 8 cores on a Leonardo node and together with the SRAN. Yes, I should probably, if we go back to job script. So what we see here is, so we use this cores module for the VASP CPU. But then we also needed to load special Intel compiler-related modules and also HDF5 module. And the reason is that here, in order to have all the correct dependencies, after you have built VASP, you need to have these modules loaded so that VASP can actually run. And that you need to have on Leonardo. If you are on Tetralit, you actually only need to load the Tetralit VASP module and things will work out of the box, so to say. So, and we can see what looks a bit odd here is this HDF5. So what is that? Well, if we look, at the output here, we can see we have now a file called waspout.h5. And this is a special compressed file format. And if I want to use Pi for WASP, one need to have compiled the WASP together so that it uses this HDF5. Otherwise, one cannot use Pi for WASP in order to do this basic WASP analysis. So usually, for the newer WASP installations, I always add it. Since the WASP developers, they also highly recommend that one adds it. But still, of course, I mean, you don't need to have it actually if you are happy just running WASP, getting your regular output and so on. And maybe, your run might be little bit faster, but it's probably less than a fraction of a percent or something. So I think it can be useful to have. Okay, yes, so we looked already at, we can look again at the Slurm output. Yeah, so here we can also see iter depths of a run. We see that it was running, it made 8 iterations before it was happy, and it minimized the total energy. So we had an energy difference in the last step, something 10 up to -4. So it looks like everything went quite fine. We can also have a look at this OSICAR. And here we only see the output from the iterative steps. So it's a bit shorter and briefer file to have a look at. And this can be useful, I mean, in particular, if you're running a much bigger job, then we would have been able to see this job in the queue, and we can check its progress by looking, for instance, into this OSICAR. So we can see that, okay, now it's on step 5 or so on. And we can also have a look at how the convergence seems to be going. And the main output is then found in the outcar. So here you can find all information about the calculation which was done. And it's a lot, it's lots of results. So here is really everything. And sometimes one might want to make sure that one actually was running what one thought one was running. But here we see information about the lattice type. It found a face-centered cubic cell. It is quite good for FCC silicon. But so this file will be quite large. We also see that, it found 56 irreducible K-points. So that means the K-points which were produced by using this MonCoursePack 11 by 11 by 11 K-mesh. And if one quickly wants to see how many K-points one get, you have it in this file, and you can see that this mesh, it led to totally 56 K-points. And here it also lists all of them in the reciprocal space. And so usually, since outcar is a bit tricky file to orient oneself in, so sometimes one prefer if one can use some grep commands to see if one is able to extract some interesting information. But sometimes one might need to confirm inside the outcar file exactly how that property one is interested in, how it might be spelled. So we can continue to have a quick look. So we can go to the end of the file, see if we found something interesting. Some general timing and accounting information for the job, something about memory. We can see that we have something called the loop plus. and that will actually tell you the time for your run as estimated by the VASP job itself. So if we do like this, we grep for loop and outcar, so we can see here. What is interesting here is this real-time value. And looking at these different steps, we can see that the iterative steps, they took roughly 0.0 something seconds. So that is quite fast. And if you're working now on a tetralit, you can compare. And I assume probably on tetralit it would be a little bit slower since it's an older CPU. So that would be my guess, but still pretty fast probably. Yeah. And the loop plus value, which we see here, that is the summed up total time for these smaller iterative steps. And maybe I could mention here also that if you're doing some benchmarking and tests, so of course that will probably be a bit larger problems than this one. But then you might need to watch out if you want to use these loop values directly, because it depends a bit. For instance, if you are working on GPU, you want to make sure that you rather use the wall time instead. Because the reason is that you might have some extra time, which is, it could be due to the GPU starting and stopping and so on. But anyway, if one only uses these loop values, one should at least check what is the total wall time for one system. And if you were on tetralit, so if you are on tetralit and after a job has finished, you could use the ceph command and the slurm job ID. So now I'm Leonardo, so it will not work because ceph isn't installed, I think. Yeah. But if we were now on tetralit, we would actually get some basic statistics about our job. And from there, we could get the wall time. And that would be probably the best property to use in some kind of benchmarks. And well, since I started to talk about benchmarks, I should also mention that it really depends a bit on what you're interested in, how you construct a benchmark. So what I typically do, if I have some very heavy jobs, which will run maybe for a day or more, that in some cases you don't really need to run the whole job, but it can be enough that you run to a certain number of iterations or run to a certain specific step, and then you compare the timings for these different steps instead of running a job which maybe takes a day or so. So that is just a thought there. Okay, yeah, so I will continue. Yes, so we finished this job and it looked like it was running quite well. So let's go down now here to the next. So go back to the main folder. Okay. Yeah. Yeah, we found that it was here. So now we're going to calculate total energies of these silicon systems. So between 3.5 to 4.3 angstrom. And to do this in a bit faster way, because if you, I mean, of course one can do these things by hand, but if we do this 10 or 100 times, our hands will get quite tired. So it's quite useful to use some script instead for these more tedious tasks. So here I have prepared a script called getWool.etot.sh. And by the way, I should say if you're working on tetralit, you're very welcome to just click on the tetralit box, and we could follow the same exercise, so to say, because apart from some that we sometimes use slightly different analysis tools, otherwise these examples are quite similar. So yeah, I should probably have mentioned that right at the start. And we might also switch a bit between Leonardo and tetralit depending on what to show. Okay, so we had this script. Let's have a look at it. Oops. Okay. Yeah. No, I should first show you the run script. Yeah, I was surprised it was a bit short, but that was because I showed the wrong script. So I first wanted to show you the run script. So run.sh. Yeah, so we can see it looks quite similar to the more simple job script we had before. And here is some simple bash scripting. And what it will do is basically it will loop for this and do a VASP calculation just for these different lattice parameters. Yes, I forgot to mention one thing about these job scripts and running on Leonardo. So it turns out on Leonardo, if we have a binary which is compiled like the hybrid, both with OpenMP threading and with MPI, then we explicitly need to set some variables so that the binary will actually run. And you can see here maybe the most important one is that even though this binary is compiled with the OpenMP threading, for the moment we are fine with just using MPI ranks. So therefore we set this parameter ompnum threads equals to 1. So we don't use the OpenMP threading in this case. And since I started to mention OpenMP, I could say that OpenMP for VASP is mostly useful if you have very, very heavy jobs and you have a problem to run your jobs because of the memory. Then an idea could be to reduce the number of MPI ranks and instead expand so that you have more threads. So for instance, if you started with 32 MPI ranks, so you could go to 16 MPI ranks and 2 open MP threads per rank, because every OpenMP thread is per MPI rank. So with 2 OpenMP threads, so it would be 16 times 2, 32. So you would effectively use all cores of the 32 core node. And also you could further reduce the MPI ranks and further increase the OpenMP threads in order, depending on how much memory you need to save. And this can be quite useful if you have very heavy calculations. And this was also introduced with the newer VASP 6 version. At least, yeah, for VASP 5, I think, yeah, maybe it was more like a test of OpenMP. Yeah, okay, anyway, so yes, we have the script here. So let's see, it should now just be possible to submit it, and this one might take a little bit longer in the queue. So we will see here. Oops, so SPurge. And I will see if I have this SQ command somewhere here so I can catch it before it finishes. So SQ -u and then your username. Yes, now we were able to catch it. So here we can see that the job is running, has been running for 11 seconds. Still running. So let's see what it's doing. Okay, it's almost finishing. Yeah, I saw there was a question in the chat here. How is the scaling with the AMD nodes for VASP? Is there a major difference with the Intel ones? Yeah, let me think about it. I think it's probably with the VASP calculations, one typically the number of cores on a CPU might be something to have in mind. So typically VASP works, I don't know if one should say more efficiently, but typically for VASP you prefer to have fewer cores and more RAM per core in general, rather than have really, really many cores with less RAM. But it might depend a bit. So there is no MKL. Well, you can actually run MKL on AMD CPUs, so that is possible.
They also have their optimized libraries, so that is not an issue.
Yeah, so there is one thing you need to watch out if running MKL on AMD, and that is if you're using the what are I called, these more architecture performance parameters. So they are basically switched off. So the higher ones are switched off for AMD, but by using some simple tricks, you can actually turn them on again and use them also on AMD. And I would say that if you have an AMD system, you really, one should do that. That is recommended. But so maybe we will, So, but so there is some work around this for AMD. Okay, I see that the job finished and it created this file summary with FCC. Okay, and here we see a list of total energies for the different lattice, and this will be possible to plot in different ways. So here, for instance, on Leonardo, I suggested one could, for instance, use GNU plot, and then one could copy this file back. And on Tetralit, you could plot it directly, and you will see, you will get the actual plot in the virtual desktop environment and have a look at it. And soon we will have a break again quite soon. We'll see if I'm did it. So GNU plot. Now we are in the GNU plot terminal. And so we need to set it to PNG to produce a PNG file. And we set our output to this file. And now we can plot it. And we see that a file was actually produced. But now the clock is 3 sharp. So I think we take a 15-minute break. And I guess we proceed to a slightly more loose session. Since some time was lost in the beginning, so I guess I will finish this first example. So I will continue to show it for people who are interested. Okay, so I saw there were some more questions in the chat. Since we were a bit late with the guided session, so I thought I should at least go through this first example. So I think I will just finish it. And then we go over to the more free part. So I saw here there were some discussions in the chat about MKL. There might be that on MKL that there are other things one can do to get good performance. It could sometimes it depends a bit on the software also. So one might need to try a bit and see what works best. But if you have AMD systems, so AMD CPUs, you can for sure use Intel MKL, but you also might need to fix that you can use these more optimized parts. And there are ways to get around this. And if you if you might remember, if you have been in the business long enough, that there was a similar thing, I think, in the beginning of the 2000s, that you had Intel compiler suits, and if it found that it was not running on Intel, it would switch off some parts, so it would typically not run as efficient. So that might be something to consider. And I see there was a question about potential files. It depends a bit on the cluster. So if your cluster is providing VASP and they are giving access to it to you through your license, there will typically be documented where you can find it. And I see that Louis put here in the chat. That's a path to where you can find the latest potential library on Tetralit can be found there. At least that one should have the correct permissions, hopefully. Okay, let's see. Were there any more questions here? And probably we could put some of this information in the HackMD also, so that we save it probably. Okay, so let's see. Well, so welcome to the second part of a hands-on, and this should typically be the more free version. But since I spent some extra time there in the beginning of setting things up, I thought, well, we can at least finish the first example, and then we will see how it goes with things. And before a break, we saw that we produced a figure here. And what you can do if you come to this step on Leonardo, so you can copy, using secure copy, you can copy this figure back to your local station and have a look at it, if it seems any reasonable. If we want to have a quick look on it directly in the terminal, we can use the so-called dumb terminal, which shows you stuff directly in ASCII. So let's see. I could just show that quickly, I think. So just a sec. I think I put it in the example under useful tools and for GNU-plot. We have GNU-plot. And we use the so-called dumb terminal. And we plot it, so we can see something here directly in the terminal. Of course, it will look nicer checking the figure. And I will go back to the example. And on Tetralit, you should be able to get a plot directly using GNU-plot via FinLink. So you will get it in a new window. Okay, so let's see here. Yes. And we can see even in this ASCII plot, we can see that equilibrium lattice constant seems to be around somewhere 3.9 ångstrom, right? And what we can do is using a so-called equation of state method in order to get a more exact value now from these calculations. And a popular method is the Birch-Murnaghan, not sure exactly how to pronounce. And here I prepared some scripts. So using ASE to have a look. And on Tetralit, one can load the ASE and Python module in order to use it. And on Leonardo, you can use these modules which were provided. Okay, and there is also a script to more easily harvest the data. Okay, but I follow the steps here for Leonardo, and I think we should have, in PAW already. If you do module list, the module available, sort out for that. Yes, here we can see this Python VS. So this one. Oh yeah, mouse is not working, but yeah. But yeah, it should. Okay. So I loaded it with a short command, is quite useful. So ML for module load. And I also mentioned if one, so this is a bit general Python environment which I prepared. So it also includes Py4VASP. And actually, when installing Py4VASP, you also get ASE automatically because it's one of the dependencies which Py4VASP will install. And then I also mentioned that just to check that one has some reasonable Python. Yeah, it seems to be the Python which was prepared in the environment. And hopefully it worked out with changing the group there, because it was only the podcar files which were protesting when I did that. So hopefully things are working fine here. Yeah, and there was a script available to save some time. So this one, get wool etut, we can have a look at it. Yeah, so it basically fetches information. So for the volume and energy from the vasbrand.xml file. Yeah, so that can also be useful to mention that, so if we are looking at the output files, so we can check. So we can see there is an XML file which contains lots of information here. And XML is this particular tagging format or language, which is quite often used because it's easier to handle data and information in this way. And also other codes are also using XML. So it's relatively common. And also in VASP we have it. And it means it can be easier with programming to handle data when it's prepared already in this format. Yeah. Okay, so let's see here. Yes, we had this script. And we should just run it because we did all these calculations. So from the previous run, we created all these other directories. So for instance, 3.9. And we can also confirm. So the difference was that we had the other lattice constants here. So here it was 3.9 angstrom, but otherwise the calculations were similar apart from that. Okay, so we should just run it. Yeah, I think. And it produced a file. Small etot. Yeah, so here we have volumes and total energies. Okay, and now there is another small Python script called ecos.py. So it uses ASE. You can have a look. Yeah, so this is so we are using the equation of state functionality within the ASE collection of Python scripts. And one can actually do quite many things with ASE. So that is one of the tools I would recommend to have a look at. One can, for instance, handle the structures also. Okay, so this is a small script. And to run it, we can just type Python and its name like this. Yeah, and here we got some output for the equation of state. And when we looked into the script, we saw that it was using this Birchmer-Nagan option, but you also have several other ones which could be used. So that could be one thing to try out, to choose some other ones and see what does one get from it. Yeah, so we got minimal total energy and bulk modulus and a volume from it. And here is also a recipe. So how to find, so here we should mention that this V0 here, that's a volume for a single atom. So, but we want to have a lattice constant. So we need to calculate it a bit. And then we remember that in the FCC cell, we have 4 atoms. So then we have a certain expression for so how we can compute it. And this, so if you follow the instructions on the web page, you can see this. So one needs to take this V0 times 4, and then one take the cube out of it, or yeah. And one idea to calculate it quickly is to use Python as a calculator. We can use that. And here I will just copy paste from the exercise. Yeah, so we see it was 4 atoms, so 4 times V0, and then it should be the 1/3, so we cube root out of it. And we got some value here, so 3.87 something, right? Okay, so that is one of the first parts of this exercise. And it continues. So where we suggest that one uses this equilibrium value and compute a new round for this. So maybe 3.875 should be close enough, I guess. And so first I will exit Python. Oops. Okay. Yeah, wants to exit that way. Okay, so so we already prepared this folder, SEF1. So we can go there. And now we want to use this value and run this job. And we already had the same job script as before. That's when we was running the very first job. Yeah. And just oops, I will make a change. So this is just a change for me. So you should still keep TD, but I will use this other project. Oh, now it takes a bit longer time. Let's see. It's in the queue, but it has at least some high priority, it seems. And I think if I remember correctly, there was some message from Leonardo that some of these days there were some nodes which were offline, so it wasn't as many available, maybe. Yeah. Or maybe I should try the TD project instead.
I think the TD project has some priorities because we are working on the
Okay,
workshop.
has it some better priority, maybe?
Yeah.
So I can try to cancel this one.
Yeah.
So do like this. Now it should be gone. And let me see. Yeah, put it back. Let's see if, well, it has some priority at least. Oh, or let me see now. I also need to check, was this maybe what was the one I canceled? Yeah, that was the one I canceled, right? So maybe it took some time before the files appeared. Let's see, did it manage to... Oh, it actually finished. Yeah. So it finished actually. Interesting. Okay. And if we follow the exercise, here are some different things one can check directly from outcar. So one can grep like free energy, and that should be the what it iterates towards, I think. And if one remove one space, one will get each of the iterative steps. And some more small tricks. So if one is looking at OSICAR, and grips for F equals, then you also get the final results. And looking at those steps, one can just have a look at OSICAR, how it seems. And important, as I mentioned before, it's quite useful to look at the Slurm files. So in the top, oops, maybe I do like this. So in the top of them, we can see a bit information from Slurm. It mentioned that HTF5 module was loaded. It told a bit about that this was running on 8 MPI ranks. It was using 8 cores in the job. And some other information it found, like a postcard, it's using Scalapack and so on. And in the last step, we just see the same information as we saw in the OSICAR file. But if there are certain warnings or cautions, they will typically show up here in the Slurm output. Okay, and let's see, finally here I had a comment. Comparing with the equation of state result, does it look reasonable? So let's have a look. So we had the total energy like this, and we were running maybe again Python 4.88029. Yeah, maybe roughly okay. So this run is a quite fast one, and the K mesh wasn't so dense. So what one can do here is, of course, to try a bit with denser meshes, for instance, to compute the equilibrium volumes one get for that. And one could also try to adjust these energy cutoffs. And these are these extra tasks which are described here. But I think I will probably stop here. So finally stop, I guess, with the more guided session. But we, or at least I, will be around until 5 o'clock. So we can have a look. So you're very welcome to continue with the exercises and ask questions if you encounter some problems. And also if maybe there are some special tasks which you're interested in. And I can remind, so if I stop sharing the terminal and I share the yeah, I think you can see it, right?
Yes.
Yes,
Yeah.
I can see it.
Okay, great. Yeah, so you have all the examples here. And of course, I mean, if one is just starting with VASP, I think it's a good idea to just follow the pace of these examples and try the different things out. And if one already is a bit familiar or have some specialized interest, and one doesn't find, for instance, well, a certain method one is interested in, one is welcome to have a look at. So you have these more examples and topics, and at the VASP wiki, you can find them there and choose what seems interesting. And then I also, as I mentioned before, you could start with your own material of interest, for instance, starting with the crystallography open database and using SIF2Cell, which was one of the modules which was available when we were typing this module use and this long path. So then it's possible to load this SIF2Cell module and use it on Leonardo. And on Tetralit, it's also available. You can test to try out the different tools. And if one is interested how the GPUs compare with CPUs, one idea might be, for instance, to run a job on a GPU and see how it works out. And then I also had some idea if I want to test a bit efficiency and benchmark. So